Alright, today we're going to go over chapter, I believe this is 16 with fault-based testing. This is a very important topic in software testing, although something you may not encounter very often. The idea here is we need to figure out how effective are our test cases. Are they actually effective or are they not? So far we've talked about ways to do analysis and inspect them using basically our own intelligence to evaluate them. But it would be nice if we could come up with at least a method to more scientifically give us a quantifiable estimate of how well our test cases are doing. And so what fault-based testing is essentially going to do is we're going to try and figure out if we can break the test cases by changing our test cases or our code slightly, and then if our test cases can't find them, then we're saying the test cases aren't that great. If that's a little confusing right there, don't worry, I'll explain a little more in a bit. We're going to go through understanding the idea of fault-based testing, but the real point of this is to look at mutation testing. And if you look at your project, one of your key points is to do at least one level of mutation testing. So this lecture is going to be very important. I'll try and explain what exactly mutation testing is and how you can implement it inside your program. So the book gives an analogy with marbles. I actually think this is probably a good idea. So don't think about testing right now. Think about you have a bag of marbles, but you know that there's a lot of them in there and you simply just don't want to count them. Is there another way we can estimate how many there are? Well, let's say for the sake of argument, you actually have 100 marbles, maybe of the same exact size, so they take up the same amount of space, but a completely different color. What happens if I mix them? Well, let's say I had 100 black marbles and none of the other marbles were black, but they were the same size. So we put them in the bowl, we stir them really, really well so that we would have even distribution when we start pulling them out. Let's say I pull out 100 at random, and 20 of them ended up being black. How many marbles were in the bag to begin with? Well, think about this. If 20 of them were black and you added 100, that essentially means that each 20, or 20%, equates to 100. So the other 80% is really 4 times the number of black marbles, or in other words, 400 marbles. So that's a way to estimate that your original bag is 400. Of course, now your bag has 500 marbles in it. Well, actually back down to 400, I should say, because you drew out 100. But now it has 80 black marbles, where originally it should have just had no black marbles. But anyways, this is an interesting way of estimating how many marbles are in there. Now, couple key tricks here I want you to make sure is we're assuming probability here, even distribution, which is an assumption of the mutation testing we're going to talk about. So right here, right off the bat, mutation testing is not going to be perfect, but it's definitely going to give you a ballpark figure about what's going on. So let's go ahead and if this example was a little complicated, please again step back and think about it. We put in 100 black, we put in 100 black marbles, and then we drew out 100 marbles. Only 20 of them were black, so each 20 represents 100 in this case, and so the other 80 non-black marbles would represent 400. Go ahead and think about this a little. I think this analogy is probably going to be helpful in understanding why mutation testing is important. Because now, instead of marbles, I have a program with bugs. So your bag is your program, and each marble inside of it is a bug. So how can we do the same thing? Well, let's add 100 new bugs to it and make 100 copies of my program, each one with one of the new bugs. So you have your original program, and then you have 100 copies of that program, each having one bug that you add to it. So each program only has one bug. You're not combining the bugs. You're only having one bug. Now you run your test suite on each of those 100 new programs, but it only revealed that 20 of them were faulty. What does that say about your test case? Well, the other program copies did not fail. That pretty much ensures that your test case is it's probably not capturing enough of the bugs in your program. So this is this is a different way to do testing, because now you're testing the tests, right? You're trying to figure out how good is your test suite, and you're doing that by creating programs that you know should fail the test suite, and then seeing if your test suite captures that. Alright, let's go ahead and go through these basic assumptions. We like to judge the effectiveness of a test suite and finding the real faults by measuring how well it seeded the fake faults. Great. valid to the extent that our seeded bugs are representative of real bugs. All right, so that's the little insight that we have to apply. Unfortunately, well, there is actually some automation tools that you can use for mutation testing. If you go out there and you look, it will come up with a couple of ways to automate mutants for your code, which is actually pretty helpful. Not necessarily identical. Black marbles might not be clear marbles, aka certain bugs may not be the same as other bugs. But the idea of mutation testing is that it's going to give you a ballpark figure. If you're getting only 20 out of 100, not good. If you're getting 95 out of 100, you're probably doing pretty good. So a mutation testing, what is it? A mutant is a copy of a program with that syntactical change, that seeded bug. Again, you have your, talking back, you had your bag with the marble. Each marble now represents a program with one bug. So a marble in that representation is a mutant, because a mutant is a program with one bug added to it. A lot of times it's very simple. Maybe instead of I is less than 0, you change it to I is less than or equal to 0. Simple change. It's great to make these changes very easy to spot or very simple, and then see if your test suite goes through and test it. In this example specifically, this is great for testing corner cases, and mutation testing is also pretty good for that. You run the test suite on all your mutant programs. Those 100 programs, each only has one bug. A mutant is killed if it fails at least one test case. Obviously, not every test case needs a test for every bug, but if somewhere in your test suite you say that the program is failing, then you kill the mutant, which is good. If many mutants are killed, you infer that the test suite is also effective at finding real bugs. The key word there is infer. Obviously, we can't guarantee it, but we can at least give us confidence that our test suite is doing well. So mutant testing uses seeded faults as black marbles. Does it make sense? What do you have to assume? Well, it must be true of black marbles if they're to be useful in counting the bowl of pink and red marbles. All right. Oh, it doesn't tell you. Okay, what must you believe here? Does this make some sense? I believe it does make some sense. I've answered most of these questions earlier. It's giving you a good ballpark figure. One thing it's going to go through momentarily is that there are a couple of things that could happen that may make your mutation testing, make your test suite look bad, but in fact it's okay. So some assumptions. Competent programmer hypothesis. Programs are nearly correct. Most programmers code for the happy path. I understand that. Real faults are some variation, or the fact that your user did something unexpected. Mutants are reasonable models of really buggy programs. In other words, if your program's really buggy and you haven't been coding it right, mutants are going to probably find it pretty quick. Then there's the coupling hypothesis.